Hello, welcome to the first systems equation for applications of Newton's second law. What we're going to do is figure out the tension in each of these cables and use Newton's laws to do that. So we have two buckets. This is the 200 kilogram bucket, and below it is the heavier one. And we have two strings, so two strings means two separate tensions, so T1, T2 like that. And the question is find each tension. So this thing's being lifted upward, raised, with an acceleration of 0.5 meters per second squared. So I'm going to call upward positive, and the key to this is recognizing that when you have a system, and by system I mean more than one object, so two, they're going to have the same acceleration because they're attached. So notice that, if I were to pull up with different accelerations, if this had a different acceleration, it would hit into this or fall down, but we're raising the two of them at the same time. So to find the tension, first I will do free body diagram, because that's going to tell me about the direction of the forces and what's going on. And literally I cannot do this problem without this step, because I need to know what's going on. So this is for the 200 kilogram block. We have tension upward like that. We're going to have the force gravity of the first block down, and then we have the second tension pulling it down because we have this acting on it as well. So for the 300 we have gravity, little gravity, so reliable, and then tension. It's the second tension because it's the second string like that. So there is our free body diagrams. Now we're going to do our expressions. So we don't need to specify x and y in this because they're just directional in terms of one direction, that is. So we'll just say up is positive, down is negative. Now if we have two free body diagrams, so we have two of these, we're going to have two equations to describe them. So here's for the first one. T1 is positive minus FG1 minus T2 equals MA. Now it's going to be M1. I'm going to call this bucket 1 and bucket 2 instead of the 2 300, but they mean the same thing. Now this is, you got to be careful with this because people mix these up, so make sure you specify that this is all for the first bucket, or the 200 kilogram one. And recall that FG is equal to MG at any point. So the second equation, we have T2 up, gravity down. So notice what I'll do, M2A. Now A doesn't need an indice because they're going to share this acceleration. So looks like I could find T2 pretty easily, because right now if I try to solve this I have two unknowns, T1, T2. But this I have all the knowns because I do have the masses. So I'm going to find T2 first. So if you see that I move that over, I get T2 is equal to M2A minus FG2, which is M2A minus M2G. And remember that trick I showed you, M2 can come out, so we have A, and I said these were added. Let me just clarify that. Okay, that's added over, plus G. Good. Otherwise it won't come out right. So the numbers look like this. So 300 is the bottom bucket. 0.5 meters per second squared is the acceleration. We add it over to the 9.81. When you do that, we get our answer of 3,093 newtons. So that's our first answer. Now for our second answer, step 4, I'm going to find T1 with our expression. So T1 is going to equal, I'm going to move these, add these both over, M1A plus MG1. So I just made that into MG instead, but this is the same thing, plus T2. What does this look like? Now you can't take out M's here because there's not an M common here, so that stays the same. So 200 kilograms, the first acceleration. I mean, you can take it out over here, but don't worry about that. Plus 200 second acceleration plus our tension 2. 3093 newtons. So let's do that. $200 times 9.81 plus 200 times 5. So I get 5,155, just like that. And just to verify, I believe those are our numbers. Perfect. Very good. So that is the first systems problem. Let's do another one. Why not? They're so much fun. So let's do kind of like what we did, but now we have a different scenario. We have two blocks, and they're held at the same height, and this is determine the acceleration of the system after it's released. Okay. So the difference is we have one string, which means we have one tension. So T is the same on both sides. Now, the other thing that's a little different is the fact that we now have to pick a direction. So I'm going to say that the heavier one is the one that's going to pull the system. So I'm actually going to call this I'll draw it up here. This direction of acceleration positive. So that means because it's attached. So if this is down, then this side's going up. So this side will be the positive acceleration. So when I do my free body diagrams, because if you see what happens, this thing will rise and do that. So that's what I'm calling the positive motion. If I went this way, that would be a negative motion. Okay? So watch what I'm going to do. I'm going to call 1, 2 for our masses. Just like that. So let's do the free body diagram of mass 1. So mass 1 looks like this. So I have gravity acting down, G1, and then I have the tension. That's it. That's all we got. This one, we got gravity, but a different one. It's a different mass, and then we got that. Deceivingly simple, right? But remember that this is the upward direction here, and this is the positive direction. Sorry, positive and positive. So when I write the expression for this one, it's going to be T minus, I'm going to just write this as M1G equals M1A. Now we have to set it to MA because the system is accelerating. So it's not rest, it's not 0. And it's common to forget that. But watch what happens here. I said that this direction down was positive, so I'm going to write this one first. Minus T equals M2A, because we're in the second block. This is block 2, this is block 1. I'll just rewrite it like that. Alright, so now we have two expressions, but oh no, we have two unknowns. We don't know T or A. So we can do a trick. We can add equations together. And you're like, why in the world would you do that? Well, watch what happens. I'm going to add this equation. Yes, you can do this to this equation. And, like, literally add them. Crazy, right? Fun math. Alright. So, what does that do? Notice that T is positive here and negative. They cancel. We get rid of an unknown. Fabulous. So, what we get is M2G minus, we got to keep that minus, M1G. That's it. Equals M1A plus M2A. So, Now remember those tricks. These are common, so I'm going to take the g out. So I get m2 minus m1, the heavier minus the lighter. And the a's are common, so the a will come out. And then I have the addition, m plus m2. So, solving for acceleration, basically I just divide by all of that. m2 minus m1, all divided by the sum of the two, equals a. And there we have it. Not too bad, right? So let's plug in some numbers, because people like numbers. So mass 2 is 3.2 kilograms, minus 2.2. 3.2 plus 2.2. Now, it doesn't matter what order I add them in. I flipped it, but that's okay. I knew that going into this. So acceleration will be 3.2 minus 2.2 times 9.81 is 9.81. Okay, divided by the sum of the two. Perfect. Acceleration, 1.82 meters per second squared. Just like that. Now the acceleration is going to be going in this direction. That's the direction of our acceleration, or in the direction of the heavier one. Now I like solving this one on the video too, because this is the Atwood's machine problem, which is very common. Not sure if you will do this in lab, but you might, in which you will basically do the same kind of theory. Also, I'm pretty sure there's a homework problem, if not exactly like this or just like this. So this is how you can solve that up. Now, as always, you can put numbers in whenever you want. I just like to solve things symbolically when I do it. So let's take a look at the last systems problem, because this one looks very scary, because now we do have two directions. We have to pay attention to that. Again, we're accelerating, so we're going to set everything equal to ma. So let's see how we solve this. Same thing, FBD of each block. This one and this one. This is the... So same thing, I'm going to call my acceleration positive if it's going in that motion, okay? Which means that for m1, I have basically force gravity. It's on a surface, so I'll have force normal, and then I'll have a tension. And since it's the same string, I can leave that as T like that. So that's my expression here, or my FBD for the guy on the table. For the guy that's hanging, it's going to be tension up, and then it's going to be 1 FG2. So common mistake is mixing these up, so just be careful. Alright, so first of all, notice that these don't contribute to our acceleration, because first of all, it's not going up and down, and secondly, the acceleration's in the x. So this yields a very interesting result. The motion, which is what we care about, the acceleration, is basically the tension, just like that, or the force. And this is all for the x direction, and that's it. So I'm not considering that. Yes, I could write the expression if you want to see it. It looks like this. There we go. Like I said, it doesn't even contribute. So let's take a look at here. So remember, I said down is positive, which means that my gravity is going to be positive, and then my tension's negative, equals to m2a, like that. So writing this as m2g minus t m1a. So notice that I plugged in t from over here, our unknown, right? And you can see I can find an expression for acceleration, so I'm going to add that over. And my time is going to run out, but you could see that I will get something that's like this. And there you have it.